welcome to episode 7 of Maths in an Empty Classroom with me, Mr. Sutton. Today we're going to be looking at the second example on statics of rigid bodies, ladders. So if you haven't looked at the first example, which is episode 6, I recommend that you go back and watch that video before looking at this one. However, what I do recommend that you have a go at doing, if you have looked at lesson 6, is pause the video, have a look at this example, see if you can work it through yourself, see what issues you come up against, and then play the video and watch the explanation. Right, here we go. A uniform ladder of mass 40 kilograms and length 12 metres rests with its top against a smooth vertical wall and its base on rough horizontal ground. Okay, so as we've been exploring with these videos, we've got smooth vertical wall, so no friction, rough horizontal ground, so friction between the ladder and the ground. The ladder rests in equilibrium at 58 degrees to the horizontal, with a man of mass 85 kilograms standing on the ladder at a point 7 metres from its base along the ladder. So that's talking 7 metres along the hypotenuse, if you like, of the triangle rather than 7 metres horizontally from the bottom of it. So let's begin by putting this into a diagram and working out what we've then got to do with it. Right, so we've got a smooth wall, rough vertical ground, and we have a ladder like so. Top against the vertical wall and its base along rough horizontal ground, so we'll call that A and B. So we have A and we have B. We were told that the angle of inclination was 58 degrees, which is that distance there. We were told that the overall length of the ladder was 12 metres, so let's draw this line here that's the same length as the ladder. I'm going to partition into the different lengths that we've got. Right, we've got it's uniform, so its weight is acting entirely at the centre, and its weight was 40 kilograms, so I've got a downward force weight of 40g there, and that is splitting the distance perfectly in two. So I've got a 6 metre distance there and a 6 metre distance there, which I'm not labelling just at the moment for reasons that you'll see. The reason for that is that we also have a man of mass 85 kilograms standing on the ladder at a point 7 metres from its base along the ladder. So let's go back to here, because in addition to this 40 g-force, we also have a force of 85g, which is the weight of the man, so that's 85g. In terms of distances, what I'm just going to label is that that's an extra 1 metre along my ladder, and therefore I have 5 metres left at the top here. Other forces to consider, let's talk about what's going on at the wall. The wall is smooth, so there's no friction to consider, but there is a reaction force acting perpendicular to the wall that the wall exerts on the ladder. Similarly, down at B, B is resting on the ground, so there's contact, so we have a reaction force at B, going like so, and because the ground is rough, we have friction between the base of the ladder at B and the rough horizontal ground. Now again, we consider what if the ladder were to slip? Well, it would do this, which would mean the base would move to the right, so friction, opposing direction of motion, must be acting to the left. So there is my frictional force there. Refer back to the question. The ladder rests in equilibrium at 58 degrees to the horizontal, 7 metres from its base, have I been told? I have not been told the coefficient of friction. Okay, so I'm on to starting the question, having labelled all the forces that I know are operating on the system. Part A, the magnitude of the normal reaction force and the frictional force exerted by the ladder on the ground. So for this question here, ladder on the ground, I'm looking at what forces are going on here. I want to know RB and I want to know the frictional force. Now, if we remember that we always have three things that we do. We do moments, we resolve vertically, and we resolve horizontally. Now, let's look at what's happening vertically, first of all. If I resolve vertically, I can see that this is actually quite nice. The only force acting upwards is the reaction at B, and the two forces acting downwards are the weight of the ladder and the weight of the man standing on the ladder. So 40G plus 85G, which means that our reaction at B is 125G, which as a number, using 9.8 as we do in maths, is 1,225 newtons. So that is the magnitude of the reaction that we've been asked for. What we're now asked for is the magnitude of the frictional force. What I'm now going to do is I'm going to resolve horizontally. And horizontally, again, I can see I've only got two forces to consider here. I've got the reaction at A that's going to the right, and I've got the frictional force that's going to the left. And what that tells me is that the reaction at A must be equal to the frictional force. At the moment, that isn't enough information to find out what friction is as a number, as a value. So I know it's equal to the reaction at A, but I don't know what it is yet. So moments. Now again, when you take moments, if you take moments about a point where there's forces acting, it's possible to ignore those forces. So I'm going to take moments about B, which means I can ignore the reaction at B, and I can ignore friction, which is one of those forces that I don't know. So I'm going to do moments about B. Again, considering clockwise moments and anti-clockwise moments. So which forces are attempting to make the ladder tilt this way if I'm pivoting about at point B? Well, as you can see, it's the reaction at A, but I need the perpendicular distance that that reaction force makes with this point here. So I need this length here. Okay. Now that is going to be equal to 12 times by sine 58. So 12 is the hypotenuse, and I'm looking for the opposite distance. So my first moment, my clockwise moment, is the reaction at A times by 12 sine 58. And I'm not going to work that out as a number yet. I'm going to leave it like that. Okay, anti-clockwise moments then, pivoting on B, what's trying to make it go this way? Well, it's two forces, it's 85G and 40G. Now 85G is a distance of 7 from the point that I'm taking moments about. I need to know the perpendicular distance between the line of action of that force and this point. So 7 meters times by cos 58 is going to get that for me. So 85G times by 7 cos 58. And the 40G, the hypotenuse is 6, but it's still the adjacent side. So that's going to be plus 40G times by 6 cos 58. Now, what I can do is actually, because it's all cos 58s and g's, I can collect that all together to be a single term. So 7 times 85 is 595, I believe, yes it is, plus 240, which is 40 times 6. So I have 835 g cos 58. And that is equal to reaction at A times by 12 sine 58. That's a number, that's a number. So if I divide 835 g cos 58 by 12 sine 58, I will get the reaction at A as a number. So I'm just going to do that now. Times by 9.8 times by cos 58. And then I'm going to divide it by 12 sine 58. And it comes out as 426.108. Now the reaction at A wasn't what I'm trying to find to answer part A of this question. I'm trying to find the friction, but as you can see, when I resolved horizontally, I worked out that the reaction at A was equal to friction, and therefore I can say that, okay, so the frictional force which is acting at B is 426 newtons to 3 significant figures. Done. Okay. Right, let's move on and have a look at part B. The minimum value of the coefficient of friction between the ladder and the ground that would enable the man to climb to the top of